You should now understand the relationship between current, voltage and resistance in a simple closed electrical circuit. In this lesson, we will look at some more complicated circuits with multiple resistive loads in series and in parallel. More than one resistor can be connected in any one circuit, and they may be connected in series, which is one after the other, in parallel, which is alongside each other, or in a combination of series and parallel. You will find the symbol shown here in a number of electrical circuits. It is used to signify that a battery is being used as a power supply. The longer line signifies the battery positive terminal, and the shorter the negative. You are already familiar with Ohm's law. There are two more laws that you need to know to help you understand what is going on in series and parallel circuits. These are known as Kirchhoff's laws. Kirchhoff's first law states that the total current flow into a point on a circuit is equal to the current flow out of that point. Or, to put it simply, what comes out equals what goes in. In the diagram shown here, there are two current flows, I1 and I2, into point X. So the current flow out from point X, I3, must equal I1 plus I2. Kirchhoff's second law states that if all the voltage drops in a closed circuit are added together, their sum always equals the voltage applied to that closed circuit. We will look at this second law in a moment. If a number of resistors are connected in series, they will act as one long resistor. You know that the resistance of a material is directly proportional to its length. So to calculate the total resistance of a number of resistors in series, the individual resistances are simply added together. In our example here, the total resistance of the circuit, RT, will be the sum of R1, R2, and R3. If we add some numbers to the circuit, you can see that the total resistance of this particular circuit is 4 ohms plus 6 ohms plus 10 ohms, making a total of 20 ohms. The applied voltage is 12 volts. To calculate the current flow in the circuit, Ohm's law can now be applied. I equals V divided by R. So the current is 12 divided by 20, which equals 0.6 amps. This current will flow continuously through all three resistors. We can use this circuit to prove Kirchhoff's second law. If we apply the current flow of 0.6 amps to each individual resistor, we can establish the voltage drop across them. R1 is 4 ohms. So, using Ohm's law, V equals IR. The voltage drop across R1 is 4 multiplied by 0.6, or 2.4 volts. The voltage drop across R2 is 6 multiplied by 0.6, or 3.6 volts. And the voltage drop across R3 is 10 multiplied by 0.6, or 6 volts. According to Kirchhoff's second law, the sum of these voltage drops should equal the applied voltage of 12 volts, and it does. Series connection of loads is impractical, because individual resistive loads cannot be individually controlled. Also, the failure of one resistor would mean failure of the rest of the circuit. Parallel connection ensures each resistive load is individually controllable and receives the same voltage. Failure of one resistor will not affect the operation of the others. Most aircraft loads are connected in parallel. When we connect resistors in parallel, they act as a single resistor with an increased cross-sectional area. We know that resistance is inversely proportional to the cross-sectional area of the material, and as the total cross-sectional area will be bigger than that of even the resistor with the largest individual cross-section area, the total resistance of a number of resistors in parallel will always be lower than the resistance of the lowest individual resistor. The total resistance of a number of resistive loads in parallel can be calculated using the formula 1 over the total resistance, RT, equals 1 over R1 plus 1 over R2 plus 1 over R3, and so on. In the circuit shown here, R1 is 4 ohms, R2 is 6 ohms, and R3 is 10 ohms. Using our formula, 1 over RT equals 1 over 4 plus 1 over 6 plus 1 over 10. You will recall from your school maths training that to solve this equation, we need to find the lowest common denominator for 4, 6 and 10. This is 60. So we can rewrite the equation as RT equals 15 over 60 plus 10 over 60 plus 6 over 60. 1 over RT equals 31 over 60. To get RT, we need to invert this, so RT equals 60 over 31, or 1.94 ohms. We can now use Ohm's law to calculate the total current flow in the circuit. I equals V over R, or 12 over 1.94, which is 6.2 amps. We can check this calculation is correct by looking at the current flow through each resistance individually. Using Ohm's law, the current flowing through R1 is V divided by R, or 12 divided by 4, which is 3 amps. The current flowing through R2 is 12 divided by 6, which is 2 amps. And the current flowing through R3 is 12 divided by 10, which is 1.2 amps. According to Kirchhoff's first law, the total current flowing in the circuit, IT, is the sum of these three currents, which is 6.2 amps. The same answer as we got when we used the total resistance. Now you can try one for yourself. Work out the total resistance of this circuit, enter it in the box, and press Go. To calculate the total resistance of a circuit containing resistive loads both in series and in parallel, we first calculate the resistance of each parallel group, and then add them together with the series resistors. In the example shown here, We will first calculate the total resistance of the parallel resistors R2 and R3, then add it to R1. Using the formula for parallel resistors, 1 over RT equals 1 over 6 plus 1 over 10. The lowest common denominator for 6 and 10 is 30. So we can rearrange the calculation to say 1 over RT equals 5 over 30 plus 3 over 30, or 8 over 30. Inverting this gives us 30 over 8, which is 3.75 ohms. To find the total resistance in the circuit, we add this to R1. So the total resistance is 3.75 plus 4, making a total of 7.75 ohms. The arrangement of resistors shown here is called a Wheatstone bridge. The Wheatstone bridge can be used to compare an unknown resistance, in this case Rx, with others of known values. It is used in a number of measuring instruments, and its use is fully explained in the instrument lessons. That is the end of the lesson. The important things to take from this lesson are the formulas for working out the total resistance in series and parallel circuits. These formulas are being displayed on the screen. Remember that in a circuit containing resistive loads both in series and in parallel, we first calculate each parallel load, then add them to the series loads.